Okay, welcome back. So here we are, we're looking at Unit 9 for the final exam review. And our first few questions here, 1 through 3, they're asking us pretty much to take words and convert them into what we call a skeleton equation. Basically, that means to write the chemical symbols for each reactant and each product. And there are some keywords that sometimes give us some hints, such as reacts with, tells you what the reactants are. In this case, it says it's zinc and aqueous iron 3 sulfate. So let's get right down to business. Zinc, we know, is a chemical element, so it's symbols just from the periodic table. Aqueous iron 3 sulfate. Aqueous just means it's dissolved in water. So we can indicate that with symbols if we wish. But here we got an ionic compound. Iron 3 is a metal, right? It's the iron plus 3 version of iron combining with sulfate. So one of the strategies we looked at in class was to crisscross the ion charges to determine the ratio. Let's get a different stroke thickness here so we can do this a little more efficiently. Okay, so we're going to bring a 3 down to SO4, right? And when we bring that 3 down to SO4, that means we need 3 SO4s. We're going to bring a 2 down to iron. So when we go to write the formula, we require 2 iron. Since SO4 is an ion made of multiple atoms, we got to put that in parentheses because there's more than one of them. And we said there are 3 of them. And let's make these look the way they're supposed to look. So SO4 are the symbols for the ion sulfate, and there happen to be 3 of them. Okay, so there are the reactants. Little reaction arrow there. Now let's look at what it says our products are. It produces iron, right? Produces is a keyword. Iron is produced. So we know that we're just going to write the symbols for the element iron right from the periodic table. And another compound, aqueous, dissolved in water. Look at this ionic compound. Again, it begins with a metal, right? Where am I getting these charges from? Zinc is 2 plus and sulfate is 2 minus. Well, we're looking at the ion chart here. When we look and we find zinc on the chart, right? Zinc is, where is it at, Mr. Brewer? Is it not on here? Oh, there it is up here, 2 plus. Sulfate is 2 minus, SO4 2 minus. So they're coming from this particular resource. So zinc, oh, look at that. The charge is already canceled. So let's not bother crisscrossing there. Let's say we need 1 zinc and 1 sulfate, and let's make the symbols for sulfate look correct by giving it the little subscript 4 instead of the crazy looking 4. So there's our skeleton equation. Okay. In our next example, hydrogen gas reacts with. So again, there's the keyword reacts with, right? Our reactants are hydrogen gas. Just keep this in mind. Elements that end in gen or ine are always diatomic. They are always molecules, not atoms. So hydrogen gas gets written that way, H2. That would stand for oxygen, nitrogen, right? Chlorine, fluorine, bromine, iodine, those end in gen or ine. It reacts with nitrogen trifluoride. Now we don't have ions. The reason we know that is nitrogen is nitrogen trifluoride is a compound that does not contain a metal. So it uses prefixes in its naming. Nitrogen suggests there's 1. Trifluoride suggests there's 3 fluorine. So there's our reactant, nitrogen trifluoride, right? We're going to want to put the reactant arrow. I'm sorry, the reaction arrow. Nitrogen trifluoride. Well, what does it produce? Look, it says it produces nitrogen gas. Again, nitrogen is an element. It ends in gen. So that guy, right, we reflect it as diatomic. It's a molecule, never an atom. And hydrogen monofluoride, 1 hydrogen, mono, that means 1 fluoride, hydrogen monofluoride. There we go, skeleton equation. Our next example, sodium oxide reacts with water. Well, sodium oxide is made of 2 ions, right? The sodium ion plus 1 charge, the oxide ion minus 2 charge. So we need, when we look at the formula, we need 2 NAs, 1 O. It says that reacts with water, H2O, y'all know that. So let's make the formulas look the way they need to with the subscripts. And there we go. There's our reactants. Well, what does it form? Well, when we read the words, it says it forms an aqueous solution of sodium hydroxide. So what we want to do then is look at, for the ions, sodium and hydroxide. We go to our chart, right? Sodium is +1 right here. Hydroxide, OH -1, right? +1 and -1, they already cancel each other out. So let's just say we need one of each of those. So we go to write this formula for it, NaOH, one of each ion. That's how we suggest it in formula version. Okay, number 3 is a whole bunch of different ionic compounds. Lead-2 nitrate mixes with potassium chromate. So I went to our ion chart and I got all of the charges of the ions that I needed to perform this. So when we read this one, lead-2 nitrate +2 and -2. I'm sorry, we got that wrong. Nitrate is -1. So when we crisscross that, look at, we're bringing a 2 down to NO3, we're bringing a 1 down to lead. So when we go to write the formula, 2 NO3s, 1 lead. Next chemical that is a reactant, potassium chromate, that's the K+ ion and the CrO4 - ion, right? Again, bringing a 1 down to CrO4, bringing a 2 down to K. So let's add that, right? 2 down to K, 1 CrO4. Notice CrO4 is not in parentheses now. We'll make our little reaction arrow. Let's make these look the way that I like them to appear. And there's our reactants. Now our products, right? Those ions break free when they form products. They turn into 2 new chemical compounds made of the same ions, just in a different combination. KNO3, right? Potassium nitrate, aqueous solution of potassium nitrate, +1 and -1. That means we need 1 K, 1 NO3. And then our last product is lead-2 chromate. So lead-2 chromate, right? We need 1 lead and 1 chromate because the charges cancel each other out, +2 and -2. And there's our symbols. So somebody might be wondering, well, why does it say NO3 and 2 outside of parentheses on the left side, but on the right side it doesn't? Well, that's because this is only the skeleton equation, not the balanced equation. So we would put coefficients in front of each reactant and product to make the quantities balanced. Skeleton equations show the correct formulas. Balanced equations include coefficients that show the correct ratios. So that leads us to this item 4, balancing. So the first example, there's no real particular strategy that works for this one, but when I look at the chemicals, I see that there's 3 chlorine on the left and only 2 on the right. So I want to try to choose a coefficient to put right here in front of BaCl2 to make the same quantity on the left side. So there's actually no whole number I'm going to be able to put here that will make 3 of them. So what I'm going to do is I'm going to think about where 3 and 2 would first meet up. They'd meet up at the number 6. So this will make 6 Cl on the right. There's only 3 on the left. So a 2 would create the amount of Cls we need on the left. And we got to go back and double check everything else. This also doubled the amount of aluminum, or Al. So there's 2 Al on the left. We need 2 Al on the right. This 3 that we placed here made 3 barium, or Ba as well, which means we need 3 barium on the right. And our coefficients 3, 2, and 3, 2. So that's a balanced equation. In part B, there is a strategy that kind of works. You want to try to recognize ions and group them together when we see polyatomic ions. So here's what I mean by that. I see CrO4 on the left side. I also see it on the right side. That's the ion called chromate. The fact that it's not in parentheses means there's 1 of each on the left and the right side. I also see ClO4 on the left side. in parentheses, but on the right side, not. So on the left side, there's 2 ClO4s. On the right side, there's only 1. So now we can begin fixing this. So ClO4, we know we need 2 of them, right? Because there's 2 on the left side, but only 1 on the right. So coefficient of 2 is a good start here. That makes 2 NAs as well. Oh, look, we already have 2 NAs, so nothing to do with that. CrO4, there's 1 on the left. There's also 1 on the right. Calcium, there's 1 on each side. So this only requires 1 coefficient. 1, 1 makes 2, 1. So 1, 1, 2, 1 are the coefficients that work. In item C, this is a combustion reaction. There was a hint for a strategy we talked about in class that said, hey, let's do the oxygen atoms as the last element when we do these combustion reactions. So we recognize this combustion because oxygen is a reactant. So let's balance our carbon right away. 3 on the left. Let's make 3 carbon on the right. Ignore what that does to oxygen. 8 hydrogen on the left. Well, we need a multiplier of 4 to make 8 on the right. Let's add up sum total of oxygen now on the right. 3 from CO, right? Because 3 times the 1 for CO makes 3. 4 from water. 3 plus 4 is 7. So there's actually no whole number I can put on the left side that I would multiply this 2 by to make 7. But sometimes we can use a half piece to help us. So if I actually multiply 3.5 times 2, it is balanced at the quantity 7 and everything's balanced. But most people don't prefer to have those halves in there because we don't really have halves of particles. So we eliminate the half by multiplying each coefficient by 2. So all of these coefficients are going to change. The 1 becomes a 2. This 3.5 is going to become a 7 because we're multiplying it by 2. Right? This 3 is going to become a 6 because we're multiplying that by 2. And then the 4, when we multiply that by 2, becomes 8. And it ends up balanced with 6 carbon on each side, 14 oxygen, 6 from CO, 8 from water, and 16 hydrogen. 2 times 8, 8 times 2. So we got a balanced chemical equation. Okay. Letter D, it doesn't really look like there's any particular strategy that works. So let's just kind of do a trial and error method on that. So I see 2 H's on the right, but 3 on the left. So we want to try to get the H quantity the same on each side. So I know 3 and 2 will meet up at that value 6. So 6 H's on the right by placing a 3. 6 H's on the left by placing a 2. We just got to double check what this does to nitrogen. 2 N's on the left. Oh, there's already 2 N's on the right. So there we have it. Coefficients 2, 1, 3. That balances that guy. Letter E looks like there is a strategy that works. We see the NO3 ion on the left side and on the right side. We see the SO4 ion on the left side and on the right side. So what we do see is NO3 is in parentheses and there's a 2 outside. And over here on the right side, NO3 is not in parentheses. So on the right side, there's 1 NO3. On the left, there's 2. Well, let's fix that. Coefficient of 2. That makes 2 NO3s on each side now. 2 Ks on the right because we multiplied by the coefficient 2. There's already 2 Ks on the left. Calcium, there's 1 calcium on the left, 1 calcium on the right. SO4 or sulfate, there's 1 on the left, 1 on the right. Hey, this is balanced with coefficient 1, 1, 1, 2. Looks like we got a combustion reaction again. This one's a little trickier. So let's see what happens with this. So when I look at this guy here, let's see. I see the H's are already balanced, but the C's are not. So let's try to put a 3 here. That'll balance the carbon amount. What we're going to notice, 3 times 2 is 6 oxygens. But there's also 1 oxygen from water. 6 plus 1 is 7. Just be careful on the left side here. Isn't there already 1 oxygen here, but 2 here? So if we want a total of 7 on the left for oxygen, check this out. Placing a 3 here makes 6 plus the 1 that's over here in this molecule already. There's 7. It's balanced now. 3 carbon on each side, 2 hydrogen on each side, 7 oxygen on each side. And there's our review of balancing. Okay, our next example is asking us to review the types of chemical reactions. So I have some markup going here already. One of the special types of reaction we called, let's do these in an order that I think makes better sense. So let's take a look at the example right here on the NH3 plus H2SO4. Look at the little note I wrote here, one product. There's no plus sign and there's no other chemical written after that. So anytime that we see there's one product, that's a synthesis style reaction. We call that synthesis. That's the identifying feature. Opposite to that, we might have one reactant. I know this one wasn't in the examples that I gave you, so I placed one there. So here we see there's one reactant. Anytime there's one reactant and it breaks down and forms multiple products, we call that a decomposition style reaction. So synthesis and decomposition, they're completely opposite of one another. Okay, so let's look at the differences between these two examples, Li3N and the PB example here. So the example right here, we see we have 2 compounds. Well, these 2 compounds trade some parts. The Li was attached to N and the NH4 was attached to NO3. If you look on the other side, we get 2 new compounds to form. So 2 compounds form 2 new compounds by swapping some ion parts. That's always called double replacement, the swapping of ions to make 2 new compounds. Now you got to make certain that you're not just looking for 2 compounds. You look for swapping. Li is now attached with NO3. NH4 is now attached with N, and that's what identifies it as double replacement. In the example below, there is swapping that occurs, but the reason that we call this one single replacement has to do with what participates in the swapping. There's always an element in a compound as a reactant, and it forms a new element and a new compound when the swapping happens. So PB was alone, but on the right side, it attaches to a compound with PO4. H was part of a compound on the left, but now it separates itself and becomes the element. That's what identifies that, a single replacement. An element and a compound form an element and a compound. The easiest of these to identify is typically the combustion reaction. Oxygen will be listed as a reactant, and that's what I wrote here, a little hint. Look for O2 on the reactant side. That identifies it as a combustion reaction. That leads us to the last example up top. It actually is swapping of 2 compounds, so we could probably call this one double replacement. There's a better answer because the H ion comes together with the OH ion. It forms water. When a double replacement reaction forms water, that's called a neutralization reaction. So that's probably a better way to categorize it. There's an acid and a base that are neutralizing each other. And we recognize when the H and the OH ions come together. And that's why this water molecule forms here. So our last example on this page, oh, look at that, compound. They swapped some parts. That's another example of double replacement. Okay, our next example asks about the solubility of some chemicals in water. So we would consult our solubility rules for that, this chart, right? Solubility rules, we're not memorizing it, we're using it like a tool. Na2SO4, so we generally look for the second part to use it more efficiently. The SO4 are called the sulfates. Let's see what it says about sulfates. All are soluble unless it's attached to calcium, strontium, barium, silver, or lead, right? So this is not one of those. So we would call this soluble. The next example, oh, sulfate with calcium, that was on the list for exceptions. So we would call that insoluble. Let me show you what I mean. Back to the solubility rules. Most sulfates are soluble unless it's calcium, right? This example that we have is calcium with sulfate. So we call that insoluble. And that's why I chose to write that there. Letter C, just be careful with letter C. There's a little detail in that one. So we're going to look for PO4 or phosphates. Look what it says. All the common phosphates are insoluble unless a group 1A ion is attached to it. In this particular example, K is a group 1A ion. It's in group 1A called potassium. So instead of that being insoluble, that guy is soluble. So we'll look for the next example, ClO3, right? They're called chlorates. Look what it says, chlorates. All the common chlorates are soluble. It doesn't list any exceptions. So let's just call this guy soluble. Our next example, Cl, those are called chlorides. Look what it says about chlorides. So our chlorides, all common chlorides are soluble unless it's silver, lead, copper, or mercury. So this is not an example of silver, lead, copper, or mercury. This is potassium. So we can assume this chloride is soluble. And then lastly, there is a chromate, CrO4. Let's see what it says about chromates. All chromates are insoluble unless it's a group 1A ion or it's ammonium. Well, this example is not in group 1A. This is lead. So we know that this is not one of the exceptions. We call that insoluble. That solubility chart really helps us make predictions about products that would form. So when we have a double replacement reaction, one of the easiest ways to do double replacement would be to name the two chemicals. So you'd consult your ion chart and you'd name this. So we know this first one is named sodium sulfate, right? NaOH, excuse me, sodium hydroxide, my apologies. I'm on a sulfate run here for some reason. The two ions are named sodium hydroxide, right? You can consult your ion chart if you need to, this guy here. And aluminum is attached with nitrate, aluminum nitrate. Well, here's what happens. When double replacement occurs, the positive ions, the metals trade places, and we get two possible new identities, sodium nitrate and aluminum hydroxide. Now, what we want to do is we want to look at the solubility rules and see if either of these make an insoluble chemical, because if one of them does, then we know a reaction happens. If neither of them, right, if they're both soluble in water, these two new products, then we just write no reaction because nothing really happened. So it turns out aluminum hydroxide is not soluble in water. Hydroxides are insoluble and aluminum's not an exception. So we're going to write products for this one. And we use the charges of the ions to do that. So when we look at the charges of the ions, right, sodium is +1, nitrate is -1, aluminum is +3, hydroxide is -1, and that's what we're going to use to write our product symbols. So our product symbols, Na with NO3 ion, +1 combined with -1. Right? This symbol is soluble, or this chemical soluble in water. You can look at the solubility rules to determine that. The nitrates are always soluble. And we look at the other chemical, right? Aluminum hydroxide, we already determined that that is not soluble in water. So we write the formula for that. And we could either use the symbol S for solid or the symbol PPT to say, hey, here's a precipitate that forms. So we get products to form, and that's why we write new formulas. The products get pushed right up against the reaction arrow, and here is what happens for that particular chemical. So sodium nitrate forms, right? That's what NaNO3 is. And aluminum hydroxide forms, that's what AlOH3 is. And this stuff over here really just helped us determine the answer. Okay. In part B, right, we're going to see, we'll name the chemicals. We have something called copper sulfate. Again, I looked at the ion chart to determine that. We have something called potassium chlorate. We're going to swap some parts, right? When those parts swap, we're going to see that we get something called copper chlorate, and something called potassium sulfate. And we look at the solubility chart, the chlorates and the sulfates. Chlorates are all soluble. Sulfates are mostly soluble unless it's one of these metal elements attached to it. Well, it's not in this case. So in this case, neither of the chemicals are insoluble in water. That means no double replacement reaction happens. We can just write NR. Nothing really happens. Let's skip C for now. We'll come back to that example. So if we look at letter D, we got calcium nitrate. And we got potassium chromate. We're going to swap some parts to get two new possible chemicals and then check solubility. So when we swap, we get calcium chromate. And we get potassium nitrate. We're going to consult the solubility chart, chromates. So let's look for calcium chromate. Chromate, oh, insoluble. So we know a reaction happens here. Let's write our products then, because calcium chromate's not soluble and potassium nitrate is. So we know we got a precipitate to form. So we'll use the charges of the ions. Calcium is +2. Chromate, CrO4 is the symbol. Its charge is -2. Right? Potassium nitrate, K, is a +1 charge. O3 is a -1 charge. So we're going to write the products. We're going to need one calcium ion and one chromate ion. The +2 and the -2 just cancel each other. Right? That guy is insoluble. So we'll give that guy either the S or the PPT symbol. And then the other product, 1K and 1 NO3. Right, that guy's going to get the AQ symbol. So there we have the products that form as a result of what we call double replacement. So double replacement, you consult the solubility chart, right? If both of the possible chemicals that form are are soluble in water, then you write NR like we did for this example, no reaction. If one of them forms a solid because it's insoluble, then you got to write products. So let's take a look at letter E, right? We got sodium chloride. Reacting with lead-2 nitrate. We're going to swap some parts. Oopsie, having trouble typing here. And now sodium is going to attach itself to nitrate if it can. And lead-2 is going to attach itself to chloride. So let's look at our chart for chlorides and nitrates. Chlorides, right? All are soluble. Oh, unless it's lead. I think we have lead here, don't we? Lead with chloride. Oh, okay. So we know that we're going to get a precipitate to form. That means we got to write the products. Let's look at the ions and their charges. Sodium is +1. Nitrate, NO3 is -1. Nice, easy formula to write because there's a +1 and a -1. Lead-2, when you look at your ion chart, is a +2 charge. Chloride, Cl, is a -1 charge. So we'll go right to writing those formulas. Na, 1 Na, 1 NO3. That chemical is soluble in water, so we give that the AQ symbol. Pb, but now we're going to need 2 chlorides, right? That chemical is not soluble in water, so we either give that the S or the PPT symbol, right? And there's our products, right, for that particular example, right? We get products of sodium nitrate and lead-2 chloride. Okay, if we were to consult the solubility chart, we're going to see copper phosphate, right? Copper and phosphate, when they join together, right? We have copper 2 in this case. That's going to be one of the possible products because this copper ion attaches itself to this phosphate ion. And sodium is going to attach itself to sulfate. So in this example, we got a phosphate that has copper attached to it. Phosphates insoluble unless it's a group 1A ion. Well, copper's not a group 1A ion, right? So we got to write the formula for that by knowing the charges of the chemical. So let's say copper is +2. Phosphate, PO4, is -3. Sodium, I know, is +1. And sulfate, SO4, is -2. We'll crisscross those charges to come up with formulas. And then that means we would need 3 CUs, but 2 PO4s, right? We decided that was insoluble, so that gets the S, the PPT symbol. And then sodium with sulfate, 2 NAs, 1 SO4 based on the charges, right? Charges are down here. 1 we're crisscrossing, right? 1 comes down to SO4, 2 comes down to Na. And that guy we decided was soluble in water. So that guy keeps the aqueous symbol. And, you know, we could change these subscripts to make them look the way that we wish them to look. So you swap the ions, right? And sometimes by swapping the names, that's maybe the easiest way to go about doing this. What I meant was I didn't show you the names being swapped in this one. This one starts out with being sodium phosphate. It reacts with copper sulfate. Right, we swap the sodium and the copper, we get copper 2-phosphate and sodium sulfate as a result. Okay, the example that we skipped here was a strange style of double replacement where we got H2SO4, we could call that hydrogen sulfate, and KOH, potassium hydroxide, right, comes from our ion chart. We're going to swap, right? We would get something called hydrogen hydroxide. It's really not hydrogen hydroxide, but I'll talk about that in a moment. And we could get something called potassium sulfate. So this thing, hydrogen hydroxide, is really just the H ion and the OH ion. Look at that. Doesn't that look like a water molecule? That's because that's what it is. So sometimes double replacement reactions form water. That's a neutralization style reaction. We don't have to look at solubility, right? Because we know it made a product called water. And then potassium sulfate, we'd consult the ion chart. We would know that the charge of potassium is +1 and sulfate is -2. So we get 2 Ks, 1 SO4, right, based on the charges of those 2 ions. And that's how we go about predicting the products of that guy. Okay, let's move onward to some tools for single replacement reactions, predicting those products. So we want to see which elements are more reactive than aluminum. So we got a tool for doing that. Let's pause this video for just a moment so I can locate that. Okay, here's our tool. It's called activity series. So we want to know which element is more reactive. Let's put the actual assignment up here. More reactive or less reactive than aluminum. So we're comparing all of these to aluminum. We just look at their position compared to aluminum's position. Excuse me. So aluminum's up pretty high. So any element that's below aluminum on the chart is going to be less reactive than aluminum. And any element that's above it would be more reactive. Basically, this allows us to make single replacement reaction predictions. And we'll look at some examples of that in a moment. So let's fill in the information. Since lead is below the activity series for aluminum, lead is less reactive. Silver is also below aluminum. So silver is also less reactive, right? Sodium is above it. So sodium is more reactive. Hydrogen is definitely below it. Hydrogen is less reactive than aluminum. Potassium is definitely above it. So it's more reactive than aluminum would be. Let's just double check barium. So let's peek at the chart. Barium compared to aluminum, right? So we're going to peek at our chart, barium and aluminum. Now in this particular chart, it's not on there. But what I happen to know about its location is if we were to place it on there, let's place it on there. It would fall right in about this region. Meaning it's slightly higher than aluminum on the chart. So there it is, barium more reactive than aluminum. Okay. So we would say barium is more reactive. So that's how we tell if one metal is more reactive than another. And that's how we make predictions of single replacement reaction. So let's get right to business. Predict if a single replacement reaction happens or not. So here's aluminum, the element, trying to replace copper. Well, since aluminum's more reactive than copper, it can actually do that. So that means on the right side, copper becomes an element. It gets replaced by aluminum, and aluminum joins up with the SO4 ion, and we use the charges of the ions. Aluminum is +3, SO4 is -2. The charges of those ions tell us that we should have 2 aluminum and 3 SO4 when we write the products. So it would look in that nature. Of course, we'd make those numbers small numbers, not large numbers like that. So in the next example, here's iron, the element by itself, trying to replace lead. Well, iron can only replace lead if it's more reactive. Turns out when we look at not the solubility chart, Mr. Brewer, turns out when we look at the activity series, iron is above lead. So iron is more reactive than lead. So let's just assume it's going to be the iron +2 ion when we go to write the charges. So let's use the +2 version of iron. So we know lead is going to be replaced by iron. Lead goes off by itself, Pb. And then iron and nitrate join together. Iron, we said we're going to assume it was the +2 that formed. Nitrate, we always know from the ion chart is always -1 or minus. That means we need 2 nitrates. Right, but 1 iron. So we'll write Fe, NO3 in parentheses, the 2 outside, there's our products. Okay, our next example, check it out. Magnesium's trying to replace potassium. Well, that's never going to happen. Magnesium's lower than potassium on the activity series. Magnesium is below potassium. So we can just write, hey, no reaction, NR. Right, nothing's going to happen here. Here we got calcium trying to replace hydrogen. Well, calcium is far more reactive than hydrogen. So hydrogen becomes the element. Whenever we write the element hydrogen, we write it as H2. Remember, hydrogen ends in gen. And then what we're going to see is Ca ion, Ca, which is a +2 charge, right, joins up with phosphate ion. PO4 is phosphate ion, and it has a charge of -3. And we would crisscross. 2 comes down to PO4, 3 comes down to calcium, and we get products that look, or a product that looks like this: Ca3, PO4, in parentheses, but we need to indicate that there's 2 of them. Okay. So here's iron trying to replace the hydrogen, right? But here the hydrogen is in water. So this is a strange example. but let's just talk about it anyway. So it says that these metals displace hydrogen from water. Only barium up to lithium can replace hydrogen when it's part of water. So this is hydrogen in water that's trying to be replaced. So this actually is a really easy example. Iron can't do that, right? Only that list of elements above is possible to do that. So we write no reaction. And barium in the last example could definitely replace silver because it's more reactive. So we take the charges of the ions, barium's 2+. We know nitrate or NO3 is 1-. So we would need 1 barium and 2 nitrate ions. That should be a curve, right? And then what's going to go off by itself is the element silver, Ag. So there we have single replacement predictions. You use activity series. And lastly, in the assignment, predicting products of combustion reactions. Basically, just read the words, folks. Look for complete or incomplete. When it says complete combustion of any kind of a fuel or a hydrocarbon, the complete combustion products, are always carbon dioxide and water. If it says incomplete, similar products, but it's carbon monoxide. So this example here that says complete combustion of methanol, complete carbon dioxide, water. If it said incomplete, you would write carbon monoxide and water. And when we have hydrocarbon combustion, it is actually that simple. So I hope you found this useful for the review of Unit 9, all about chemical reactions. Until the next time, this is Mr. Brewer. Thanks for listening.